Hello and welcome to Chapter 2 of the MCAT grind in General Chem. We have periodic table here, which can be a very short description. Generally, what the MCAT wants is to you be able to use the periodic table well because they just offer you it. So no need to memorize, but you need to kind of know where each groups mean. Combining with the last chapter of atomic structure, we have each atom with their respective groups showing what they're capable of. The metals here carry a positive charge when they want to turn into a full shell of when turn into an ion, whereas the nonmetals want to gain electrons to complete their shells. What we know about metals is that they conduct heat and conduct electricity well, and nonmetals are opposite from that. Metalloids are somewhere in between. Noble gases, they're gases, and they don't need to participate in charge bondings. Lanthanide and actinide have never seen questions about them, so don't worry. They're just there for coolness sake. What we do want to know is that there are periodic table because within each period, like all the group 1 down here, all the group down here, group 1 all share similar characteristics, including the number of valence electrons they have. All the lithium, sodium, potassium, cesium, francium, and all of that fills up here, all have 1 valence electrons. So they're just 1 off from completing their shell. Remember, they all want to aspire to be noble gases. They all want to be nobles. So all the group 1 want to get rid of that 1 electron they have in their valence shell to have a full octet to become a noble gas. Well, not become, but like have the same valence electrons amount. So for all the group 2, they want to get rid of 2 electrons and subsequently become a full octet as well. On the other hand, the nonmetals, so group 17 here, they have 7 electrons in their outermost valence shell, so they want to add and gain 1 electron to complete their octet. So that's your fluorine, chlorine, bromine, and iodine. And so forth. Now, we want to memorize a couple of very important trends that often gets tested. These are effective charge, which is denotes as ZF. What effective charge you can think of is basically the charge and attraction from the valence electrons, the positive charge attraction. So lithium, how many electrons does it have? 3 in total, because it's 1, 2, 3, number 3 on the periodic table, where you read from left to right and blah 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 all the way across. So number 3, so it carries 3 protons and 3 electrons. Now, the first shell has 2 electrons, and the third shell has 1 electron. So the outermost valence electron feels a total of 3 positive charge from the nucleus minus the 2 electrons in the non-valence electron. It gets shielded. So 3 minus 2 equals to 1. So it just feels that 1 effective charge for the valence electron. Now, you will notice that very quickly, a quick way to notice the effective charge is to look at the single digit. So 1, for group 1, they all have an effective charge of 1. Number 2, they all have an effective charge of 2. And for group 17, they have, for F, it has 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electrons. 2 of them are in the first shell, so there's 9 protons minus the 2 electrons in the first shell, so that's 7. It feels an effective charge of 7 attraction. Okay, so basically the attraction from the valence electrons, and you can quickly find that by looking at the single digit from whichever group it is. Ionization energy is the energy required to remove an electron. What you know is that for the first ionization energy will always be bigger, the biggest, because when you want to pull an electron off an atom, actually no, it's not always the biggest. The ionization energy will get bigger and bigger as you pull off more electrons. Think of a radish, not a radish. What am I thinking? But it will be harder and harder to pull off more and more electrons. Maybe think of an apple tree, and when you pull off an apple, you get, oh yeah, that's pretty easy. But when you want to go and pick another, you will have to get a ladder and climb up there, and you need to exert more effort to pluck off another apple. Yeah, that's a better example. So basically the energy required to remove an electron. So what we have here is actually a special pattern we can notice, because all of the group 1 here, they do want to get rid of the electron to turn to full octet. The first ionization energy is actually very, very low to pull it off. However, to pull off another electron from lithium, let's say, you require a tremendous amount of energy because it's already at full octet. It doesn't want to give up that electron, so just don't do it. For calcium, for example, it's in group 2. You'll notice that, okay, it's hard to pull off that first electron. Yeah, you need that energy. However, the energy required to pull off the second electron is not that much higher compared to the first ionization energy. Why? Because, well, yeah, it wants the second electron removed so it can turn to full octet. I don't know exact numbers, so let's say if calcium requires 100 energy to remove the first electron, it only might need 110 energy to remove the second electron, right? Because it's completed full octet. It likes it that way. Think of an apple tree. With the first apple you pluck, it's all fine, but the second one you pluck, since there's a windstorm, the branches like kind of bendy, and by plucking off that apple, it's very favorable for the tree to get rid of that excess weight. And we have the electron affinity, which is the energy released when adding an electron. Electron affinity will definitely be high over here because they don't want to get another electron. They want to get rid of an electron. Whereas here for nonmetals, they do want the electron added to them, so they will release a certain amount of energy when you add energy to them. Okay, for electron negativity is how attracted to electrons the atom is. Well, every nonmetal here is a lot more attracted to electrons than the metals here, because metals want to get rid of electrons, nonmetals want to get electrons. So that's what you can see here. Atomic radius is just how big and the size of the atom is, so it'll get bigger when you add more electrons to them. However, there actually is a particular thing when you add electrons to it, because the same amount of protons are in the nucleus, and when you're adding it from left to right, they're still in the same valence shell. When you add the electrons, the negative charge actually pulls towards the positive charge, and the shell overall gets a little bit smaller. So actually, when you're adding electrons without adding additional shell, the atomic radius decreases. For ionic radius, it's pretty much the same thing as atomic radius. However, just a small distinction. It'll get smaller and smaller and smaller up till along here metalloids, before it actually gets big again to nonmetals, and it gets smaller and smaller again. That's the general trend for ionic radius. Now, here I've summarized the general trends. Effective charge, ionization energy, electron affinity, and electron negativity all increases from going right and up. Right and up. They all go up. However, for atomic radius, it goes down when moving left to right, and it also goes down when going up. So that's generally all I have for you. Take care.